All right, so you sent in some research on radioactive decay,
Uh-huh.
and looks like you're diving deeper than the usual two-stage model.
Right.
We're talking 3 states.
Yeah,
Wow, this stuff gets pretty complex.
it
It's
does.
not just a simple countdown timer, is it?
No, it's not. And what's really interesting is that we can look at this three-state model,
Okay.
which comes from Wolfgang Christian's work
Hmm.
at Open Source Physics at Singapore from two distinct perspectives.
Okay.
A continuous model that gives us kind of the overall picture,
Okay.
then a stochastic model that really focuses on the randomness of uh, individual atoms.
Okay, I'm intrigued.
Yeah.
So first up, we've got the continuous model.
Right.
It looks like there are 3 equations involved here,
Yeah.
each tracking the number of atoms in a particular state over time.
Exactly. And these equations are all about prediction.
Okay.
If we know the initial number of atoms and the decay rates, which are represented by the Greek letter lambda, we can use these equations to chart how the whole sample will behave.
Okay.
And this works because we're dealing with huge numbers of atoms,
Mm-hmm.
billions upon billions, so the individual randomness kind of averages out.
Yeah.
Think of it like predicting the overall flow of traffic.
Right.
You're not tracking each car, but you get a sense of the overall movement.
Gotcha.
Yeah.
So the continuous model gives us the big picture.
Yeah.
But what about those individual atoms?
Right.
That's where the stochastic model comes in, right?
Precisely. And here's the thing.
Okay.
With the stochastic model,
Mm-hmm.
we're acknowledging that we can't know for sure when a specific atom will decay.
Oh, wait.
It's all about probability.
Mm-hmm.
You know, this decay rate represented by lambda
Right.
tells us how quickly those atoms are transforming.
Okay.
Each atom has a certain chance of decaying within a given time frame,
Right.
and the model simulates that inherent randomness.
So if we can't predict exactly when an atom decays, how is this model even useful?
It's useful because it reflects the reality of how decay happens at the atomic level.
Okay.
It's not a smooth, predictable process like the continuous model suggests.
Okay.
There's an element of chance involved.
I see. So it's about getting a more accurate picture of what's actually going on.
Right.
Even if it means acknowledging that we can't know everything for sure.
Right.
Yeah.
And there's another intriguing aspect of this model.
Okay.
It allows for an atom to theoretically jump directly from state 1 to state 3,
Uh-huh.
skipping state 2.
Okay.
Now, we know that doesn't actually happen in nature.
Right.
The decay process always goes through state 2.
Okay.
But sometimes it happens so fast that we might miss it.
Wait, so wouldn't that make the model less accurate?
Well, no, not necessarily.
If it's including something that doesn't actually happen.
Think of it this way.
Okay.
Including this direct jump helps account for those cases where the decay happens faster than our ability to observe it. It's a way of acknowledging the limitations of our measurement tools while still capturing the essence of the process.
That's a really interesting point.
Yeah.
It highlights the difference between what we can observe
Yeah.
and what's actually happening at the atomic level.
Exactly. And that's why having both the continuous and discrete models is so valuable.
Okay.
They give us different but complementary perspectives on the same phenomenon.
Right.
One gives us the big picture, the other zooms in on the individual details.
I like it. So speaking of visualizing these models, there's this really cool interactive simulation you can play with.
Oh, yeah.
It's color-coded,
Yes.
so you can see the atoms changing state in real time.
Right.
And you can even tweak the parameters like those decay rates we were talking about
Yeah.
to see how it affects the entire process.
It's really cool.
It's super cool. I was playing around with it earlier, and it really helps to see how everything comes together.
It's a fantastic tool. You can actually see how adjusting the decay rates changes the populations of atoms in each state. It brings the math to life. And what's even more impressive is that it shows you both the time evolution of the nuclides
Right.
and the number of decay events per time interval.
So you can see both the gradual decrease in parent nuclides
Yeah.
and the bursts of decay events happening over time.
Yes.
That's pretty amazing.
And if you want to zoom in and focus on the individual atoms,
Okay.
you can enlarge that view as well. It's like having a microscopic lens right there in the simulation.
So this is all well and good, but for someone who hasn't thought about nuclear decay since high school,
Sure.
why should we care about these models?
That's a great question.
What's the real-world relevance of all this?
It's easy to think of radioactive decay as something that only happens in labs. But the truth is it's happening all around us constantly. From the potassium in bananas, which is slightly radioactive, to the carbon dating of ancient artifacts.
Oh, yeah, carbon dating.
Right.
I remember learning about that in school, but I never really connected it back to these models.
Sure.
It always seemed kind of mysterious.
Yeah.
Like, how do they actually know how old something is just by looking at carbon?
Well, it all comes down to understanding the decay rate of a specific isotope of carbon called carbon-14.
Okay.
By measuring the ratio of carbon-14 to other carbon isotopes in a sample and knowing its half-life,
Right.
we can estimate how long it's been since that sample was part of a living organism.
Okay.
It's a really powerful technique for archaeologists and paleontologists.
Wow, that's actually pretty cool.
Yeah,
It makes you realize this stuff is way more than just theoretical equations.
absolutely. And it goes even further than that.
Okay.
Understanding radioactive decay is crucial in fields like medicine, energy production, and environmental science.
Okay, I'm all ears.
Okay.
Give me some examples.
For instance, in medicine, radioactive isotopes are used in imaging techniques like PT scans and in radiation therapy to target and destroy cancerous cells.
Right.
And when it comes to energy, nuclear power plants rely on the controlled fission of uranium atoms.
Right, nuclear energy. It's a pretty controversial topic these days.
It is, and understanding the science behind it, including the intricacies of radioactive decay, is essential to having informed discussions about the benefits and risks of different energy sources.
I totally agree.
Yeah.
So what about environmental science?
Okay.
How does radioactive decay play a role there?
Well, one example is using radioactive tracers to track the movement of pollutants in the environment.
Okay.
Scientists can introduce a small amount of a radioactive substance into a system and then follow its decay signature to understand how pollutants spread and where they end up.
Okay.
This information is crucial for developing effective remediation strategies.
So these models, especially this three-state model we're diving into, are really tools that have a huge impact on our understanding of the world and how we interact with it.
They are, and the more we learn about these fundamental processes,
Right.
the better equipped we are to address the challenges and opportunities they present.
This has been an incredibly insightful deep dive, even for someone like me who hasn't thought about nuclear decay since high school.
Mm-hmm.
And it's really amazing to see how this seemingly abstract concept has such far-reaching implications.
It is, and it's a constant reminder that even the most seemingly niche areas of science can have a profound impact on our lives.
So true.
Yeah.
And I think we should leave our listener with something to really ponder.
Okay.
Something that connects back to that element of randomness we were discussing earlier with the discrete model.
I'm ready when you are.
Okay, listener, here's a challenge for you, Kitchet. Imagine you could observe a single radioactive atom knowing its decay rate.
Okay.
Would you be able to predict exactly when it would decay?
It's a question that really gets to the heart of quantum mechanics, and the answer is even with all the information about that atom's decay rate, you wouldn't be able to pinpoint the exact moment it will decay.
So even with all our sophisticated scientific models and equations,
Yeah.
there's still a fundamental element of mystery to it all.
Exactly. There's always an element of unpredictability when you're dealing with the quantum world.
Yeah.
It's a constant reminder that there are limits to our knowledge, and that nature at its most fundamental level
Right.
operates with a degree of randomness
Yeah.
that we can model but never entirely predict.
That's a pretty profound thought to end on. It makes you realize that even with all our scientific advancements,
Yeah.
there's still so much we don't know.
Absolutely, and that's what makes science so exciting.
Right.
There's always something new to discover, always another layer to peel back.
Well, I think we've peeled back quite a few layers today.
We have.
We've gone from those big picture continuous models
Yeah.
to the nitty-gritty details of individual atoms. And we've even touched on how this seemingly abstract concept of radioactive decay
Right.
has real-world implications in fields like medicine, energy, and the environment.
And let's not forget that interactive simulation.
Oh, yeah.
That's a fantastic resource for anyone who wants to explore these concepts further and really get a feel for how these models work.
It's definitely worth checking out.
Yeah.
Okay, listener, we've thrown a lot of information at you today, but hopefully you've come away with a deeper appreciation for the complexities of radioactive decay. It's a fascinating process that's constantly happening all around us,
Right.
shaping the world in ways we're only beginning to understand.
And who knows, maybe this deep dive will inspire you to do some exploring of your own.
Yeah,
There's a whole universe of knowledge out there waiting to be discovered.
well said. Thanks for taking us on this incredible journey into the world of three-state nuclear decay.
You're welcome.
It's been an absolute pleasure.
The pleasure was all mine. Always happy to share the wonders of nuclear physics.
All right, that's it for this week's deep dive.
See ya.
Make sure to check out the show notes for all the links and resources we talked about, and be sure to subscribe so you don't miss our next episode. Until then, stay curious.